Okay, so here's now an example of where we're actually going to use this this formula, and actually to do this question you don't need to use this formula. And my point is not to teach you how to use to do this question, rather how to use this specific formula. Okay, so what we have is a light inelastic cord connects two objects. Here they have the objects, so 6 kilogram and 3 kilogram. They are pulled up an inclined plane that makes an angle of 30 degrees with the horizontal. Okay, great. With the force of magnitude F, ignoring the mass of the string. Okay, so we don't need to consider the mass there. The coefficient of friction for the 3 kilogram and for the 6 kilogram is 0.1 and 0.2 respectively, 0.1 being for 3 and 0.2 for 6 kilogram. State Newton's laws of second motion. That's your theory. I want to get to the actual calculations. Okay, first I just want to look at this one quickly. How will the coefficient of friction be affected if the angle between the incline and the horizontal surface increase? And here you might or you might not know that we get two coefficients of friction. Okay, we get a coefficient of static friction. Okay, that is when an object is on a plane but it's not moving. And then we get a coefficient of kinetic friction. Now what a coefficient is it's a constant. What does constant mean? It doesn't change. Okay, so how will the coefficient of friction be affected? The coefficient of friction be affected, okay, not kinetic friction, but the coefficient of kinetic friction, it remains the same. The only thing that can change the coefficient of kinetic friction is the surface. Okay, different surfaces has different coefficients. Okay, so for example, the coefficient for kinetic friction for ice would be much smaller than the coefficient for kinetic friction than, let's say, a tar road. But a tar road's coefficient for kinetic friction is much less than a grass patch. Okay, have you ever tried cycling on a grass patch? Okay, it's very difficult. Why? Because the coefficient for kinetic friction, that friction is very high. Okay, now we use this to calculate the coefficient for kinetic friction. We use it to calculate friction. We take friction is equal to the kinetic friction. In other words, that's the friction that a moving object is experiencing. Friction of a stationary object is given by using the same formula, just with stationary friction coefficient. Okay, so this is the formula for kinetic friction, where the normal where N is the normal force. Okay, so as the normal force increases, okay, so as the normal force increases, the frictional force will also increase. Okay, now a normal force increase, the flatter the surface is. Okay, so for example, a horizontal normal force for a horizontal plane is equal to weight. So the normal force is equal to the weight. As the surface makes an incline, okay, it becomes smaller than the weight. Okay, why? Well, the normal force, if I go put it here, okay, there's the normal force. Okay, the normal force is the portion of the weight that is perpendicular to the surface. Okay, this the portion of the weight that is parallel to the surface is there. Now if I have, this is theta, I won't go into all of the geometry just now, and that is then, if this is theta, then that angle there would be theta. You can go work out why. Okay, that means that to get the portion that is perpendicular to the surface, I am using, is my triangle cos or sine? Cos, because I'm doing the adjacent side. So the formula here would be, oh, wrong one. The formula would simplify to, or be more accurate as mu k, coefficient of friction, times, and then this becomes the portion of the weight that is perpendicular to the surface. So we'll use cos of theta, which is that angle it makes. Okay, so that's we'll use this idea in the next question. It's only why I'm expanding it a bit now. Now, question 3, draw a labeled free body diagram. Is that a one with a picture, or is that a one with a dot? That's the one with the picture. So we must draw a labeled free body diagram for the 6 kilogram object. So now look at the 6 kilogram. Ignore absolutely everything outside of that circle. Okay? All we're going to look at is we're going to see, well, we'll always start, we'll draw our box, okay, on a surface, and now we're just going to draw in our forces. As I say, we always start with weight. So let's draw in our weight. Okay, there's weight. They said we should label it. Okay, after weight I said in a different color, in other words, and preferably in pencil, put in the change in displacement. Now, we don't know if this thing is moving. They didn't say anything, but we can see there's a string attached here. So let's just assume it's moving in that direction. Okay, so it doesn't really matter for now, but we're assuming it's going in that direction. And if you read the rest of the question, you'll see here, calculate the tension in the string if the system accelerates up the incline. Okay, so we're going to use this a little bit later. This is my direction of displacement, my dot. Okay, and the only reason why I do that is so that I can fill in all the other forces. Well, the other force is the normal force that's perpendicular. Okay, that's my normal force. I'll just label it with N. And then another force is, so you literally take your ruler and in the opposite direction you put friction. Okay, and now the question is just, is there also an applied force? Is there anything attached to this box, like a rope or some person pushing it, or is there anything attached to it? Yes, there is a string attached to it. So no matter what, there is definitely, and that string is not just lying on the ground. Okay, so there's definitely a force applied. You can either say force applied, or since this is a string between two objects, I like to call it tension. Okay, we'll call this tension in the string. Does that make sense? Okay, now for your next question, and this is now where I want to show you where we're going to use our formula. Okay, here they say the tension in the string for the next question, and by the way, this is 4 lovely marks, isn't it? 4 marks. Brilliant. For drawing. Awesome. Tension in the string, we should calculate the tension in the string, so we must calculate T in the system if the system accelerates up the incline at 4 meters per second. Okay? So brilliant. This is what I'm going to do. I'm going to start with W net is equal to the work applied, that would be the work done by tension, plus the work done by gravity, plus the work done by friction. Is there any other forces? Only normal, but we don't need to do that one. Okay, and now I can choose on this side, what do I want to replace? Am I going to do change in kinetic energy? In other words, a half mass times future velocity squared minus initial velocity squared. That's one option. Okay, change in kinetic energy. The other option is taking the net force times the displacement. Okay, that is, I'm literally using the formula for net work done is net force times displacement. Or I can replace net force with mass times acceleration. Which of these 3 do you think is going to be the best to use here?
The third one, because at the first it's saying acceleration, not velocity. So
exactly. We're given acceleration. This is lovely. Okay, I'm just going to use mass times acceleration times delta x. okay, is equal. Now work done by tension, we can see, and by the way, I forgot to do this before I start my I need to fill in my angles. They said that this angle here, I think, is 30 degrees, is it? Okay, so that one we know is always 90. This one we know is always 180. So those ones aren't a problem. It's this one. What is this angle here?
It's 90 plus 30.
Good, because that's 90, that's 30. So this one would be 120. Awesome. So the work applied, we can see work or tension is in the same direction as, they say it's accelerating up. So it's accelerating in the same direction as t. So we know that the angle between t and direction of displacement is 0. So this would just be t times delta x. Plus, now the work done by gravity is mass times gravity times, and now we would put delta x. I always forget my delta x. Please don't you also do that. Okay, it would be your mass times gravity. That gives you weight. That's the force that we're talking about here, weight, times displacement, times the angle between them. That's cos of 120. Okay. Plus, and now the work done by friction is the frictional force times delta x times cos of 180. Now, the only thing here that I'm going to delete this first is we don't know frictional force. We have to calculate it using this formula. Okay, because they give us the coefficient of friction for the 6 kilograms. So all I'm going to do is just instead of F, I'm just going to put that formula. Mu K times the normal force, which is weight, which is mass, times gravity, times cos of that angle 30 degrees. Okay, well let's put in 30 degrees. Do you understand what I did? Okay. This was just the F. This is just force. Now I still have to multiply F with delta x and with cos of 180. Is that okay? So what I did? Okay, so this is a massive formula, but look, it's for 5 marks. Okay, it's allowed to be a massive formula. Good, now we really simply just substitute. You're going to see one problem though, is we don't know how far it moved. We're never told that it moves a certain distance, but that's okay. Let me show you why. Every single term has a delta x in it, which is awesome. As long as delta x is not 0, I can divide every single term with a delta x. I'm allowed to do that in an equation, do you remember? Okay, I'm allowed to divide with everything that's not 0. Now, how do we know that displacement is not 0?
Because it says it's accelerating.
Can't accelerate if you're not moving, isn't it? Okay, so we're allowed to do it. So in the end, we left with mass times acceleration. We're working with a 6 kilogram, accelerating 4 meters per second. T is what we want. Plus mass times gravity is 6 times 9,8. Delta x we sort out, cos 120. Okay, mu they said for the 6 kilogram, I think was 0.2, was it? Yeah. 0.2. Mass is 6, gravity is 9,8, cos of 13, and cos of 180. Let's just change this to a negative. Then we've done cos of 180. We don't have to punch that into a calculator. And there you have an equation. All you need to do is solve for t. Okay, and that can't be so difficult. Okay, so 63, comma. Okay, good. That would be the tension in the string if Carl calculated that correctly. Okay, so let's hope he did. Good, but the method is correct. And if you look at this, okay, for this amount of work you got 5 marks. Okay, none of that was really difficult. Okay. This formula always works. Now, how you should have done this equation, how you should have done it is by saying net force is equal, and now you just add up all the forces. Okay? But to do net force, you have to include this angle that it makes with the net force. Okay, so it would have been exactly the same formulas without the delta x. The rest would be exactly the same. Like net force is the tension cos the tension and cos the angle that it makes with the net force. Then gravity times cos and the angle it makes with the net force, etc., etc., etc. Okay.
So for the friction, will we have to put that formula for meeting? Yeah.
Yeah. Yeah. And this formula is on your formula sheet, so it's really not difficult. All you need to remember is that well, on your formula sheet you have mu n. Okay, you need to know n is mg cos 30. Weight times it's the portion of the weight that is perpendicular to weight. Okay, so it's easy enough to remember that part. Okay, let's look at, there's another part to this question. Again, in this part they say calculate the magnitude, it's 2.4.2, calculate the magnitude of the velocity of f if the system moves up the inclined plane at a constant velocity. Okay, so now we've got, in the previous one they said that we had to calculate the tension in the string. Now we have to calculate f. Okay, now f works on what? F is attached to what? To the 3 kilograms. So we're just going to look at the 3 kilogram. If he goes at a constant velocity, this is an inelastic string. That means this thing is just going to also do 3 kilograms. So I'm just going to look at the 3 kilograms and I'm going to do exactly the same thing. Okay, look at what I'm going to do. I'm going to say, first, of course, I'm going to draw my force diagram for the 3 kilograms. Okay, I always start first drawing my my weight. Again, let's now just make sure in which direction is it moving. It moves up the incline at a constant velocity. So that is going to be, again, I just do my dot. Okay, my direction of displacement is upwards. Okay, then I draw my normal force, which you can ignore when you're not drawing a force diagram for marks. Okay, I draw in my friction. Okay, but there's another force acting in on this picture. Look at that. Look at the picture with it at this little circle I drew. What else do we have? Sorry?
F.
We have F. Oh yes, sorry. I haven't done F. So F is going to go in this direction. Good, in the same direction. But then there's something else. Can you see it? What's the difference between this circle and that circle? S. Weight. What else?
Oh, another force pulling it from that.
Exactly. Remember that this is being pulled up, but at the same time, and that's Newton's second law, that this one is pulling it down. Okay, was that third law? You never remember. Okay, but for every action there's an equal and opposite reaction, which means that there is not just friction in this direction, there's also this tension that we calculated. Okay, so there's two forces going backwards, both friction as well as tension. Okay, now with that in mind, okay, as soon as I've done this, I need to go and fill in my angles. Okay, and now you'll notice that this is 30 degrees. Everything looks exactly the same. That's still 120 degrees, the angle between the force that it's applied, okay, as well as the friction is in the opposite direction, and you see the tension is also in the opposite direction, so both of them is 180. So if I use my formula, I would say that the net work done is equal to the work of the applied force, that's work of F. Let's do that. The work done by force F plus the work done by gravity plus the work done by friction plus this additional force now, the work done by the tension. Okay, and now we just fill in that. Now, again, I've got 3 options for my net work done. Which one would you say? Should we use changing kinetic energies formula? Net force times delta x, or mass times acceleration times delta x?
Acceleration.
Why would you use this one?
We're still given the acceleration.
What is the acceleration?
If you use 4 meters.
No. Read.
Oh, constant velocity.
Constant velocity. Acceleration is?
0.
0. You can use any one of these 3, because if constant velocity, then this is 0. There's no change in kinetic energy. If constant velocity, there's no net force, because Newton's law says an object will accelerate only if there's a net force acting on it. So if it's a constant velocity, net force is 0. Using this formula, we can see, yeah, acceleration is 0. So any one of those would work. We know the net work done on a constant velocity system is 0. Lovely. Okay, so work done by the force. Remember, the force is what we want to calculate. Okay, so we have delta x. Again, we don't know delta x, but you'll see again delta x will just divide away. Even though this one doesn't have a delta x, if I divide it with delta x, it's still 0. Okay, cos of the angle between f and, a bit far from my sketch now, but the angle between f and dot is 0. So I don't have a problem there. Okay, so I don't need cos of 0, it's just 1. Okay, between gravity is mass times gravity times delta x times cos of the angle, we said was 120 degrees, plus the work done by friction. Okay, this time we are still going to use this formula for friction. Formula for friction is mass times coefficient of friction, mass times gravity times cos of the angle of inclination, which was 30 degrees. But this is just friction. Now we still have to multiply by delta x and cos of 180. Are you getting this? You understand what I'm doing? Good. And then finally we have work done by the tension, which is just tension times delta x. And what's the angle between the tension and the dot? 180. Excellent. Cool. And this is again just massive length formula, but it's brilliant. 0 is equal. We want everything. We're just going to divide away delta x in every single term. So just take it all from the beginning. Is mass. We're working with the 3 kilogram, 9.8. Delta x is now gone. Cos of 120 plus mu for the 3 kilogram was 0.1. Mass is 3, gravity is 9.8, cos of 30, cos of 180. Cos of 180, I'm just going to say that's going to make this one negative. Okay, and this one, same thing. This is just going to become negative, and then our t we calculated was 63.58 minus 63.58 times delta x, which we said we cancelled. And there you go. Okay, now I can just solve for f in the normal way. Okay, so 80 comma 83. Again, I'm trusting that you calculated that correct. Okay, if it's wrong, Carl, you're wrong on YouTube. Okay.